Good afternoon, and thank you for coming for the last afternoon session. I appreciate that you are tired, but I hope to wake you up a little bit. My name is Kostya, I work at Google, and I'm going to talk about fuzzing today. So, I hope to explain you why we should be doing fuzzing. We'll have several case studies related to fuzzing. I will discuss continuous and automated fuzzing, which is a kind of magic. And I will cover some of the challenges we face with adoption of the fuzzing. I will not cover any deep technical details today. This is just half an hour talk, but your questions after the talk about any kind of detail are very welcome. So, what is fuzzing? Let's first discuss what is testing. In most cases, testing your API means that you feed a fixed number of fixed inputs into your API and observe the behavior. On the contrary, fuzzing is a process where you are feeding an infinite amount of generated inputs into your API. That's it. And there are lots of different strategies for doing the fuzzing, or in other ways, for generating the test inputs automatically for your API. I'm mostly working on so-called coverage-guided fuzzing, but this is all irrelevant for today's talk. Today's talk covers fuzzing in general. So why would you fuzz C++ code? And please wake up. So one of the reasons why you want to fuzz your C++ code is that because hackers love C and C++. The problem with this is that the hackers love C++ and C for different reasons, not for the same reasons as you love C++. This animated GIF shows you how fuzzing can find heartbleed bug in 5 seconds. And for those of you who don't remember, heartbleed is a bug that shocked the industry, the internet, about 3 years ago. And I've presented this thing at CppCon 2 years ago. So, did I hear any boo in the audience? No? Did I really say C/C++ on the C++ conference? Boo? Anyone? Yes, I did say C/C++. Because C++ unfortunately inherited a bunch of problems from the C language. The major one, in my view, is the set of memory safety bugs, such as buffer overflows, use after freeze, uses fun initialized memory, and so on. Every time I say something like this, C++ inherited, blah, 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 I hear, boo, anyone? No? I hear that, come on, modern C++ doesn't have those things. I've heard this when C++ 11 appeared, when C++ 14 appeared, and I keep hearing it now. So I have a few things to say about modern C++, but let me say just one thing. So this is a modern C++. The class called std_string_view has just appeared in C++ 17. Who can spot the bug in this code snippet? Raise your hand. Okay, so quite a few of you can spot the bug, but quite a few of you cannot, or are sleeping. Anyone else? Okay, so that's a heap buffer overflow. We're creating a temporary object, which is a result of concatenating two strings. We take the reference to that temporary object in the string view, then the object is destroyed, and then we use the reference to the destroyed object. Oops. Any kind of sane memory error detection tool for C++ will report this bug if you execute this code while testing with this memory safety tool. Things get a little bit more sophisticated if you just remove a few characters from this example. If instead of using hello with many O's, you use hello with just a few O's, it will become a different bug, at least as it is implemented in libc++. Because this is now a short string optimization, no heap memories involved. This is still a bug, but slightly different. So, modern C++, you said. Let's fuzz some really modern C++. I don't have anything written in C++ 17 because the standard is 2 days old. But I have something written in proper C++ 11. This is a relatively small library called WOF2, which handles web fonts. I would say that 50% of you have WOF2 in your pocket, in your phone. So, it is a C++ 11 library. The team follows a strict coding style for C++ 11. The team uses code review. The team has unit tests. The unit tests are running on continuous integration. The code uses STL containers, iterators, namespaces, and even bells and whistles. It didn't help. When we started fuzzing this code, we almost immediately found a buffer overflow, which is a write of 12 kilobytes outside of the buffer. And just imagine this thing is running on your mobile phone and is processing data that you receive from internet, from untrusted sources. So you probably care about fuzzing. Do you agree? Okay, so you're not asleep. Good. And now let me show you how much effort did we spend to find those memory issues in WOF2. This was not the only memory issue in WOF2. So this snippet of code, and we call it a fuzz target. It is a single function that consumes an array of bytes and that uses this array of bytes to feed them into the API you want to fuzz. I want to emphasize, this is all the effort required to fuzz that library and to find bugs in it. And we found it with libfuzzer. You can find it with many other fuzzing engines the same way. Let me just show you how easy it is to do things with libfuzzer. So suppose you have this fuzz target in a separate file, fuzz.cc. This is fuzz.cc. And you have all other files of your library, of your API, somewhere else. All you need to do is get fresh clend. This is all pretty new development. Compile all your code, including the fuzz target, with a couple special switches. fsanitize address gives you memory safety checking, and fuzzer gives you instrumentation required for coverage-guided fuzzing, and it also adds some library at link time. Then you want to create a directory where you will put some samples for the inputs of your API. And then you just run the resulting binary on this directory. This is it. So I hope I convinced you that fuzzing is pretty simple. A few words about the concept of fuzz target as we understand it. So again, a fuzz target in our current definition is a function with a fixed signature that consumes an array of bytes. And then inside that function, you use the array of bytes with your API in whatever way you want to. The fuzz target should be tolerable to any kind of data. And any kind of crash or abort or assertion failure or timeout or out of memory should be considered a bug. If not, I would say that your code is not really an API. This fuzz target should be single process. It should be ideally deterministic. If you need randomness, get the random bits from the input. Preferably, it should not modify global state, although we can tolerate this. And the smaller the target is, the more efficient will be the fuzzing. Although we can fuzz arbitrary large targets if we have enough CPU power. So far, we discussed mostly memory safety bugs. But stability and security of an application, not necessarily of C++ application, is much more than just memory safety. Let me give you another example, which I hope is suitable for a C++ conference. 8 months ago, my colleague Dmitry Vyukov has submitted a single ticket against Boost regexp library. And this is literally the ticket. So in just half an hour, Dmitry has found memory safety issues of different kinds, assertion failures, segmentation faults, infinite loops, bunch of leaks, and so on. And this is the effort he needed to spend to fuzz, boost, regexp, and find those couple dozen libraries. Again, these are just half a dozen lines that have no complicated logic in them. All you do is you take the data provided by the fuzzing engine and you feed it into your API. And this is what you get, those many bugs. I'm very grateful to the Boost developers for fixing all of those bugs very promptly. This is great. Like not all of the developers who get reports from us fix their bugs. Boost did. But the problem was that continuous fuzzing was never set up. And I want to emphasize that continuous fuzzing is much stronger than just fuzzing, for reasons I hope you understand. These are the same reasons why testing is not enough and continuous testing is much better. So I have added Boost regexp to the continuous fuzzing service, which I'm going to talk about on the next slide. And it happened last Thursday evening because I was preparing my slides and I realized that something is missing on these slides. On Saturday, 5 bugs appeared on the continuous fuzzing service in Boost, and Sunday evening, last night, 2 more popped up, and one of them was actually memory safety bug in Boost, stack buffer overflow. If anyone here is from Boost, I will try to catch you tomorrow at the Boost dinner so that we can fuzz more of Boost. So a few words about the continuous fuzzing service I've mentioned. The service is called OSS Fuzz. We have launched it December last year, and the project is a collaboration between quite a few teams at Google. The project provides continuous and automated fuzzing of open source projects on Google hardware. It uses 2 different fuzzing engines right now, libfuzzer and AFL. More fuzzing engines are in pipeline. And the service also uses the sanitizers, ASAN, MSAN, and UBSAN to actually find bugs at runtime. This project is available to what we call important open source projects, and it's provided for free. We haven't built this thing from scratch. Instead, we reuse the same infrastructure that we're using for the last 2 years to fuzz the components of the Chromium browser. And this slide shows some of our trophies. So in less than a year, the service have reported 2,000 bugs to more than 60 different open source projects. And this is the slide from a month ago. Now the numbers are even better. As you can see, there is a usual set of suspects: memory safety bugs, buffer overflows, and use of the free. But there is lots of other types of bugs like out of memories, timeouts, leaks. The largest section comes from the tool called UBSAN, undefined behavior sanitizer. These are basically signed integer overflows and shifts by large numbers, like you're shifting left by 1,000. Someone at this conference have already asked me, so what if I don't have an open source project? What if my project is closed source? In the current form, the service is only provided for the open source projects, and we also don't accept toy projects. The project has to be significant. But all the tools used by the service are open sourced, and most of them are part of the Clang LLVM toolchain. They're fully supported on Linux and Mac, and I want to thank you. I want to thank the Apple developers for helping me to port these tools to Mac. On Windows, they kind of work, but your mileage may vary. But if you're on a Windows ecosystem, there is a service provided by Microsoft. Take a look at that one. So back to fuzzing. The examples I've shown so far, OpenSSL, web fonts, and Boost regexp, those consume pretty simple data formats. To some extent, these are bags of bytes. Not just bags of bytes, but not very complex. And not every API written in C++ consumes simple data type. So in many cases, fuzzing complex data types is very inefficient because the fuzzer creates invalid inputs very frequently, and nothing interesting happens. So let's do another case study. Let's fuzz something that consumes a very, very, very complicated input. Do you know anything that is more complicated than C++? I don't. So if we can fuzz a C++ compiler, I'm pretty sure we can fuzz everything. Let's take a look. So a compiler is typically a series of building blocks. And roughly speaking, it consists of a lexer, a parser, an optimizer, and code generator. So we first started fuzzing Clang as a thing that consumes a bag of bytes. And we found an enormous amount of interesting things. For example, if you give the compiler these 4 bytes, it will do a heap buffer overflow somewhere. And there are quite a few of those. I've shown only the ones that fit on the slide. So we've got use after freeze, we've got infinite CPU and RAM consumption, and all of those don't really look like C++ code. Would you agree? Well, the first one maybe, but the second and third one, maybe this is C++ 20, but not C++ 17. So this was annoying because, yes, we were finding bugs in the compiler, but we were not going anywhere deep in the compiler. We wanted to get into the code gen. So we started fuzzing the C++ compiler in a structure-aware manner, such that we know that we're fuzzing C++ or a subset of C++. And this is what we've got. So we have implemented the toy prototype for fuzzing where we know that that the input is a C++. And now this input that triggers an infinite loop in LLVM, it actually looks like C++, or actually it's a subset of C, but this is my toy prototype. And all of the bugs we found this way, and we found a few, they trigger something inside the deepest levels of the compiler, namely optimizer and code generator. So how do we do this? We need to provide a little bit of help to the fuzzer by implementing what we call a custom mutator. So most of the fuzzing engines typically mutate the data they consume in some trivial way, like byte flipping or bit flipping. And instead, we need to provide a function that takes the bag of bytes, parses it into abstract syntax tree or some other structure, implements one single mutation on that tree, and feeds it back to the target that we want to fuzz. And we also have a support library that does all of the above on the protobufers. A protobuffer is a library that provides AST serialization, deserialization. And we then hooked this library into Clang so that we can fuzz C++, not protobuffers. I won't go into more details now, but this was really simple, and all of this code is in LLVM trunk now, so you can have a look. By the way, fuzzing also finds logical bugs. This is mostly important for things like cryptography, compression, rendering of any kinds. And it is very easy when you have two implementations of the same thing. Suppose you have a reference implementation of some codec or crypto primitive and an optimized implementation, and you want to verify that on every input they produce the same results. All you need to do is to implement a fuzz target that would call both versions of the provided input and verify that the output is correct. We have found quite a few bugs this way in cryptographic code, and here is one example. So raise your hand if you think that fuzzing is useful. Thank you. Now raise your hand if you think it's simple. Come on. Okay, so I haven't convinced you that this is simple. But even if it were simple, simple plus useful is not necessarily widely used. And this is my pain point. I want fuzzing to be widely used because it helps get rid of bugs. And at Google, we have reached quite good adoption of fuzzing. Not good enough, we're still working on it, but we have several thousands of fuzz targets across our server-side code and Chromium and open source projects developed by Google. And this number is growing. We achieved this because there are several things about Google infrastructure that are critical here. First of all, we control the build system. And so building all those things is trivial. It's one flag. We have built automated bug finding, automated reporting, automated tracking. We have held several events, fuzzits, fuzzathons, fuzzing weeks, etc. Most importantly, we advertised fuzzing on our toilets worldwide 3 times. And I'm not kidding. What about adoption outside of Google? Here, it varies between the teams. I've just heard from one of the large C++ company here on CppCon that they are using libfuzzer. Thank you guys, but I want everyone here to use libfuzzer if it's applicable to your code. I started my career as a C++ developer 19 years ago. And one of my first managers told me, you know, Kostya, tests are for students. Students have plenty of time for tests. We're serious developers. We're developing a production thing. We don't have time for tests. It was before Kent Beck declared his test-driven development. And even now, I see many projects and products that don't really use tests. However, this has changed dramatically. How many of you actually write tests for C++ code? Yeah. If I have asked this 15 years ago, most of the audience wouldn't raise their hands. But we need to go further. Testing is not enough. In our experience, testing finds roughly 10% of the bugs, and 80% more of the bugs are found by fuzzing. And then the remaining 10% are also not found by fuzzing or testing. They're found in production by users. So I want to proclaim fuzz-driven development. This is where all your tests are essentially fuzz targets. And the continuous integration system does continuous fuzzing. And by the way, this is not specific to C++ in any way. The people in the Rust community are already doing it very successfully. And despite the fact that Rust is a memory-safe language, they do find lots of interesting bugs, and most of them are not memory safety issues. We need to make fuzzing simpler to make it more widely adopted. And we'll probably have to change the language, the IDEs, the compilers, the build system, and whatever it takes to make it super easy. We need to make fuzzing as easy as putting one word in one place in your program. And here is my proposal that is not tested and not implemented, but I want something like this to happen. Suppose somewhere in your application you have an API function that consumes data. We want to slap an attribute on that function and have it fuzzed automatically by the build system ID, CI, or whatever you have. Now, data in size is not really C++ish. You would probably agree. And so we may want something more C++ish. Maybe allow strings as parameters, or maybe allow vectors of simple types as parameters, or maybe allow any kind of types. But for any kind of types, it becomes a little bit tricky, because the fuzzer actually needs to know how to serialize and deserialize this data, and optionally how to mutate this data. And then we'll have to provide more stuff there. Now, I've mostly talked about memory safety and fuzzing. Unfortunately, C++ memory safety is more than fuzzing. You will never solve all the memory safety bugs in your application with fuzzing. So we need to do something else, and I can see 2 most important areas other than fuzzing. First of all, we do need to have support from hardware vendors, and I call this idea hardware-assisted memory safety. Good news is that one vendor has implemented and shipped hardware with very useful memory safety feature. Unfortunately, I guess almost nobody here uses Spark. Does anyone? Yes, okay. So if you are using Spark, you have a very, very useful memory safety feature. But I don't have Spark. And all other vendors have tried to implement something useful for memory safety and failed so far. So we, as a C++ community, need to put pressure on hardware vendors here. And the second large area of improvement, we need to have something that would be a statically verifiable subset of C++ that would provide some guarantees of memory safety. I don't know if this is C++ core guidelines that Bjarne talked this morning, or if this is something else. But we have to come up with it. Of course, it will help only newly developed code. For the old code, we'll have to do fuzzing, hardware assistance, and bells and whistles. So to summarize my talk today, fuzzing C++ code is very useful because it prevents bugs, and you agreed with me. And it's also simple. I hope you will agree once you try. But we also must make it even more simple, and we must make it widely adopted. Otherwise, it won't be useful for the entire C++ community. This is all of my talk, and if you have questions, please use the mic.
Simple test cases, so that some of the test cases you show are pretty complicated and some of the debugger might have a hard time. Do you have something like to simplify the test cases as much as possible after you generate them while still showing some bug?
Can we simplify the cases generated by fuzzing? Yes, most of the fuzzing engines provide some way to minimize the test input, and both libfuzzer and AFL have some such switches. The examples for the naive Clang fuzzing are minimized. You cannot remove any byte from them. And the examples for structure-aware fuzzing for Clang are also minimized. Like, the tools are not able to remove anything from them while keeping the bug.
Hi. Are you guys fuzzing the Chromium embedded framework as well as Chrome itself, or?
Do we fuzz the Chromium embedded framework? I frankly don't know. My team provides the tools and the service, and the Chromium team fuzzes their own code, so I don't know the answer. I know that Chromium project has several hundred of fuzz targets across the code base.
Okay, thanks.
So just so that I verify that I actually understand this, your whole argument here is about generating the test data to exercise the functions. As far as detecting the actual problems, the dereference of null pointers and overflows, is that all handled by the analyzers that go with the compiler, or does your setup also include things that handle that detection?
Thanks for the question. So the question is, who actually finds the bugs? The fuzzing provides inputs that trigger interesting parts of code and hopefully trigger the bugs, but we need to somehow detect them. In our setting, we use the sanitizers, tools like address sanitizer, ASAN, memory sanitizer, UBSAN. These are the dynamic bug detection tools that work together with fuzzing tools in the same process. You can use other tools available on your platform, like on Microsoft, you would probably use App Verifier or Page Heap or other things.
So with, for example, there's static analyzers that can present in the UI the sequence of events that would show what kind of problems would happen. How difficult would it be to have a fuzzer present the same kind of sequence events that shows the errors that it's reporting.
How does fuzzing results compare to static analysis results? So fuzzing results are much better because with fuzzing you can have a reproducer that triggers the bug. You can rerun it, you can replay it, you can collect the trace from debugging, you can step-by-step it. This is what static analysis tools either don't provide at all or provide in a less usable way. So in this sense, fuzzing is superior to static analysis. I believe so. We're out of time. Thanks a lot for attention, but I'm here if you have any questions.